In this video, I will be covering how to analyze linear second-order differential equations. That is, to understand when we have solutions, when those solutions are unique, and when pairs of solutions are linearly independent and thus form a basis for all other solutions. The problem we'll be looking at asks us first to check that these two functions, y1 and y2, which are x squared minus 2x plus 1 and x squared minus 2x plus 1 times log of x minus 1 are solutions to the differential equation x minus 1 squared times the second derivative of y minus 3x minus 3 times the first derivative of y plus 4y equals 0. Then we'll need to state for what initial value problems this equation is guaranteed to have a unique solution, and finally we will determine whether or not y1 and y2 are linearly independent solutions. Alright, so this is three phases. First, check that y1 and y2 in fact work by plugging them in. Second, reformat the equation to read off where it is guaranteed to have unique solutions. And finally, use the Wronskian to determine if y1 and y2 are linearly independent. So we'll start with phase 1. Let's just see if y1 and y2 even work. So y1 is x squared minus 2x plus 1, which is x minus 1 squared. Its first derivative is 2x minus 1, and its second derivative is 2. Just plugging all of this in, we'll get x minus 1 squared times 2 minus 3x minus 3 times 2x minus 1 plus 4 times x minus 1 squared. And if you combine the like terms here and factor out a 3 from the middle term, from the first part of the middle term, then you'll get 2x minus 1 squared minus 6x minus 1 squared plus 4x minus 1 squared, which combine to make 0, the 2 and the 4 canceling with the negative 6. So y1 is in fact a solution. We do roughly the same thing with y2. Its derivatives are just a little more complicated. y2 is x squared minus 2x plus 1 all times log x minus 1, which is x minus 1 squared times log of x minus 1. That makes y2 prime equal to 2x minus 1 times log of x minus 1 plus x minus 1. And the second derivative of y is 2 log x minus 1 plus 3. And all of this is done just using the product rule and the chain rule. Alright, so we plug these in now. The second derivative stays in blue, the first derivative is in purple, and the original function is in this light blue or cyan. And it's just algebra and arithmetic. We just have to multiply things through and combine like terms. So we'll basically get a bunch of terms that are a multiple of x minus 1 squared times log of x minus 1, and other terms which are multiples of x minus 1 squared. And if you run all this through at the end, you'll get 2 x minus 1 squared times log x minus 1 minus 6 x minus 1 squared times log x minus 1 plus 4 x minus 1 squared times log x minus 1, and all of those cancel. The 2 and the 4 cancel with the negative 6 again. And as an extra bit here, we have the 3x minus 1 squared minus the 3x minus 1 squared, which also cancels. So y2 is in fact a solution. And that finishes phase 1 of the problem. We have verified that y1 and y2 are solutions. We still have to do phases 2 and 3, that is checking which initial value problems have unique solutions, and checking to see if y1 and y2 are linearly independent. So let's first check the unique solutions part. So to do this, we need to just write this equation in the right format and then read off the information. The correct format is just that the second derivative of y is isolated in the sense that nothing is being done to it. So in this case, what we need to do is divide out by x minus 1 squared, and then we'll have it in this format of the second derivative plus p of x times the first derivative plus q of x times the original function equals 0, and we'll be ready to read off the information we need. So if we divide through by x minus 1 squared, we'll get that nothing really cancels from the original part of this, but the 3x minus 3 does in fact have a factor of 3 that pulls out, and that x minus 1 that's left over will cancel with one of the x minus 1s from the bottom. And so the final result here is the second derivative of y minus 3 over x minus 1 y prime plus 4 over x minus 1 squared equals 0. So our p and our q are negative 3 over x minus 1 and 4 over x minus 1 squared, respectively. And we just need these to be continuous at the whatever initial time we're trying to set an initial value for. So that means that as long as we don't try to set an initial value at time 1, we can do whatever we want and guarantee a unique solution. Formally, if a is not equal to 1 and b0 and b1 are any real numbers, then the initial value problem, x minus 1 squared times the second derivative of y minus 3x minus 3 times the first derivative of y plus 4y equals 0, with y of a equal to b0 and y prime of a equal to b1, has a unique solution. This completes phase 2 of the problem, and we're left with phase 3, which is the check for linear independence of y1 and y2. So y1 and y2 will be linearly independent if their Wronskian is non-zero on the parts where the initial value problems are guaranteed to have unique solutions, i.e. where p and q are continuous. So this is why we did these in this order in the first place. The Wronskian is y1 y2 prime minus y2 y1 prime, and we're just plugging this in from previously in the problem. So y1 was x minus 1 squared, y2 prime was 2x minus 1 log x minus 1 plus x minus 1, and then y2 was x minus 1 squared times log of x minus 1, and y1 prime was 2x minus 1. So all that's just in there, and again we just do the arithmetic and the algebra and combine everything together, and we should end up with 2x minus 1 cubed log x minus 1 plus x minus 1 cubed minus 2x minus 1 cubed log x minus 1. And those log terms cancel out, and what we're left with is x minus 1 cubed, which is not always not equal to 0. In fact, if you tried to plug 1 in, you would get 0. But 1 was specifically that value we were avoiding. 1 is not a place where p and q are continuous, so we actually don't need to worry about it. So the fact that this is 0 for x not equal to 1 is all we need, and that means that y1 and y2 are linearly independent solutions. And this finishes the problem.